is about the BORG-WARNER automatic transmission used in our subcompact cars. You'll find the information in today's film both educational and useful. That's because the basic operation of this transmission and our TORQUEFLITE is pretty much the same. Even though the shape, size, and arrangement of the hardware inside the two transmissions is different, the torque converter, the clutches and bands, the planetary gears, and even the hydraulic system have a great deal in common. If you understand how a TORQUEFLITE works, you won't have any trouble understanding this BORG-WARNER transmission. So without further ado, let's listen to what Herb has to say on the subject.
Like TORQUEFLITE, this transmission has a three-element torque converter. The essential parts of the torque converter are the turbine, the impeller, and the stator. The impeller is connected to the engine, so power input starts there. The turbine is coupled to the transmission gears, so it's the output member of the converter. The impeller pumps fluid into the turbine vanes. Notice that the fluid flow is from the outside of the impeller to the outside of the turbine. Fluid then flows from the inside or hub of the turbine to the inner part of the impeller. Now this is actually a simple fluid coupling because we left out one essential part. The stator. Fluid flowing from the inner part of the turbine is deflected by the stator. The stator vanes redirect the fluid toward the inner part of the impeller vanes at an angle that gives the impeller an added push. As long as the turbine is turning slower than the impeller, the speed of the fluid leaving the impeller pushes harder on the turbine blades and the torque at the turbine is increased. This is basically the same as a set of gears where we swap input gear speed for output gear torque. Impeller and fluid speed is exchanged for increased turbine torque.
That's a greatly simplified explanation of the torque converter, Fred. Do you have any questions?
Well, not about the torque converter, but how do the planetary gears work?
The gear set includes the ring gear, two sets of planetary pinion gears, two sun gears, and a planet carrier. But that's too many gears to digest at one time, so I'll use a simplified drawing and cover one sun and planet set at a time. In all forward gears, power from the torque converter comes in through the forward sun gear and drives the three short inner pinion gears. In turn, these pinions drive the long outer pinions, which are in mesh with the internal or annulus teeth of the ring gear. Now notice, in first gear, the forward sun gear is turning clockwise. The inner pinions are turning counterclockwise. The outer pinions and ring gear are driven in a clockwise direction. In other words, there is no change in the direction of rotation from input at the sun gear to output at the ring gear. In first gear, the planet carrier is held so that it doesn't rotate around the sun gear. The pinions are acting as idler gears, so they don't change the gear ratio. Torque multiplication is the ratio of the sun gear teeth to the annulus teeth. In second, the forward sun gear is again driving the pinions. However, the entire planet carrier is free to turn. As the planet pinions rotate, they are actually in orbit around the reverse sun gear.
Well, I finally understand why they call it a planetary gear set.
If you keep your ears open, you learn something every day. Now notice that in second gear, the planet carrier is now rotating, and the reverse sun gear is held so that it can't turn. Gear rotation is clockwise, inner pinion counterclockwise, outer pinion and ring gear clockwise. Again, no change of direction from input to output. With the reverse sun gear getting into the ratio act, the torque multiplication isn't as great, so the numerical ratio is lower than it was in first gear.
Well, what happens when the transmission upshifts to high gear?
In high gear, both the forward sun gear and the reverse sun gear are connected to the output shaft of the torque converter. As a result, the entire gear set rotates as a unit to provide direct drive. In reverse, the converter output shaft is coupled to the reverse sun gear, and the planet pinion carrier is held so that it can't turn. Power flow is from the reverse sun gear through the outer pinion gears and then to the annulus teeth of the ring gear. The reverse sun gear is driven clockwise, so the outer pinions turn counterclockwise, and the ring gear also rotates counterclockwise. So, output rotation is reversed, and the car backs up. The forward sun gear and inner pinions are free to turn, so they're just going along for the ride.
Herb sure packed a lot of converter and planetary gear information into a very few minutes. If some of it slipped by a bit too fast, I'd suggest you study this month's reference book. And don't overlook the coverage in your Cricket and Colt service manuals. They do a real good job on the BORG-WARNER transmission.
Next on the program are the clutches and the bands. They control the planetary gears. The important thing to know is what each band and clutch does to provide automatic shifts. In all forward gears, the front clutch connects the torque converter to the forward sun gear. The rear clutch is applied in reverse and in direct drive. But let's cover each of the drive conditions to learn exactly what the bands and clutches do. If number 1, first gear, is selected, the front clutch transmits power to the forward sun gear. The rear band is also applied, and this holds the pinion carrier so that it can't turn. As we saw earlier, when the sun gear is driven and the carrier is held, the pinion gears transmit the power to the annulus teeth of the ring gear. That's one way to get first gear torque multiplication. On the other hand, if either number 2 or drive is selected, the front clutch is applied, but the rear band is not. Instead, the one-way, overrunning clutch keeps the pinion carrier from rotating in the reverse direction. With the pinion carrier stationary, the low gear ratio is provided for breakaway.
Well, why have two ways of getting low gears?
The rear band provides positive low gear lockup for engine braking. In addition, the rear band is required for reverse. Herb will get to that in a minute.
I still don't see why we need the one-way clutch.
That overrunning clutch ensures very smooth shifts from first to second because it simply freewheels as the upshift is completed. It would be virtually impossible to get a smooth upshift by synchronizing front band apply and rear band release.
In second gear, the front clutch is applied, transmitting power to the forward sun gear. The front band is also applied, so the reverse sun gear can't turn. Now you'll remember, since the pinion carrier is free to turn, the outer pinions simply walk around the stationary reverse sun gear. Of course, these pinions are also in mesh with the annulus teeth of the ring gear, so it is driven at the reduced second gear ratio. For direct drive, the front clutch connects the torque converter to the forward sun gear, and the rear clutch is also applied, connecting the converter to the reverse sun gear. Since both sun gears are locked together, the entire gear set rotates as a unit. When reverse is selected, the rear clutch is applied, connecting the converter to the reverse sun gear. The rear band is also applied, holding the pinion carrier stationary. As you saw earlier, power flow is clockwise at the reverse sun gear, counterclockwise through the outer pinion gears, and counterclockwise at the ring gear. This provides both gear reduction and reverse output rotation to the drive shaft. Before we go any farther, let's get a couple of differences between TORQUEFLITE and this transmission cleared up. There are some differences in the names used for parts of these two transmissions and some internal differences in the arrangement of the hardware. For instance, in a TORQUEFLITE transmission, the rear clutch is applied in all forward gears. The front clutch is applied in reverse and direct drive only. In this BORG-WARNER transmission, it is the front clutch that is applied in all forward gears and the rear clutch that is applied in reverse and direct drive.
In addition to that, the names of the bands are different in the Colt and Cricket service manuals. In this transmission, the front band does what the kickdown band does in a TORQUEFLITE, and the rear band corresponds to the low and reverse band in a TORQUEFLITE. And in case you didn't know, our TORQUEFLITEs have two separate planetary gear sets instead of the compound set used in this transmission.
You know, I always thought a planetary gear set was a bit too complicated for me. But Now I have a pretty good idea how one works. What comes next?
The hydraulic control system, Fred. But that part of the story is on the other side of the record. All of our service manuals contain complete hydraulic circuit diagrams, like this one in the Cricket manual. At first glance, they look complicated, but don't let that throw you. Once you have a basic understanding of what the shift valves, manual valve, throttle valve, and the governor do, you'll find it a lot easier to use these diagrams to trace out possible causes of trouble. A working knowledge of these valves will also help you visualize what's happening inside the transmission on upshifts and downshifts. Incidentally, the manual valve and the throttle valve are the only ones that are affected by external service adjustments. The operation of all the other valves is automatic, and they seldom cause any trouble as long as the transmission fluid is clean and the throttle and manual valves are properly adjusted.
In order to understand automatic upshifts and downshifts, you must know what the shift valves do and how the downshift valve, throttle valve, and governor pressure control the shift valves. The easiest way to do this is to start with the shift valves and not worry about the regulator, modulator, and orifice control valves. Although these valves affect shift quality, they aren't directly responsible for gear changes. So let's concentrate on a greatly simplified version of a shift valve. Throttle pressure plus spring pressure is applied to the upper end of the shift valve. This tries to push the valve downward. However, governor pressure is applied to the lower end of the shift valve. As a result, the valve is balanced between throttle pressure at the upper end and governor pressure at the lower end. Line pressure is also directed to the central part of the shift valve. However, it doesn't move the shift valve. It's simply waiting to be redirected to accomplish an upshift or downshift. Next, let's see what happens as the transmission upshifts from first to second to direct drive. In first gear, the front clutch is applied by pressure coming from the manual shift valve. As a matter of fact, the manual valve routes line pressure to the front clutch for all forward drive conditions. In drive, line pressure is also supplied to the 2-3 and 1-2 shift valves. However, when accelerating in the low or moderate speed ranges, throttle pressure plus spring pressure at the upper end of the shift valves is greater than governor pressure. As a result, line pressure is shut off at the shift valves. As car speed increases, governor pressure overcomes the spring and throttle pressure at the top of the 1-2 shift valve. This pushes the valve upward, sending line pressure to apply the front band. When the front band applies the transmission upshifts to second. At still higher speed, governor pressure overcomes the combined spring and throttle pressure at the 2-3 shift valve. The valve moves upward, and this sends line pressure to release the rear band and to apply the rear clutch. Line pressure from the manual valve keeps the front clutch applied. With the front and rear clutch applied, the entire planetary gear set rotates as a unit, so the transmission is in direct drive.
Why is it necessary to use both throttle pressure and governor pressure to control shifts? Couldn't you use just governor pressure acting against a spring?
If you used governor pressure alone, shifts would always come at the same speed, regardless of the load on the engine. Balancing throttle pressure against governor pressure tailors the shift speeds to fit the steepness of the hill or the size of the load. It is important to remember that throttle pressure increases as the throttle is opened. Governor pressure increases as car speed increases.
Good point, Tech, and that's why, if throttle pressure is higher than specified, upshifts will be delayed and will come at higher than normal road speed. Upshifts will be abrupt and harsh, not as smooth as they should be. If throttle pressure is lower than specified, front band release will be slow and rear clutch application will be dragged out. Upshifts will come too soon, at lower than normal speed, and they'll be mushy instead of smooth but crisp.
I know that governor pressure depends on car speed and isn't a service adjustment, but what's the scoop on throttle pressure and throttle valve adjustment?
Throttle pressure is controlled mechanically by a cam acting on a downshift valve. The spring connects the downshift valve to the throttle valve. There is also a throttle valve return spring at the far right. This illustrates the cam position at closed throttle. The throttle valve shuts off the line pressure port, so no throttle pressure is applied to the shift valves. At closed throttle, governor pressure controls upshifts and downshifts. This is the cam position for part throttle. The cam has pushed the downshift valve and throttle valve to the right. This opens two throttle valve ports, so that throttle pressure is directed to the 2-3 shift valve and through it to the 1-2 shift valve.
At full throttle or kickdown, the downshift valve and throttle valves are pushed all the way to the right, opening the kickdown ports to line pressure. Full throttle pressure is sent to the shift valves. This causes a forced downshift to second or low gear, depending on car speed and governor pressure. When throttle pressure is applied to the shift valves, it holds back the upshifts so they come at higher road speeds. The more the throttle is opened, the greater the pressure on the shift valves. At moderate car speed, governor pressure is relatively low, so opening the throttle can provide a part throttle downshift, just like our TORQUEFLITEs.
Actually, the regulator and the modulator valves modify the pressures applied to the shift valves. However, you can't do anything about adjusting them, and Herb's greatly simplified explanation should give you a practical understanding of why and how throttle linkage adjustment affects shift performance.
Are you going to tell me how to adjust throttle pressure?
That's one of the things that this session has been leading up to, so try and stop me. I'll demonstrate on the cricket over there. The first thing to do is to make sure the carburetor throttle is fully open when the accelerator pedal is still 3/8 of an inch from the floor. If the pedal hits the floor, you won't get any forced kickdown. Now we're ready to check throttle pressure adjustment. The Cricket and Colt manuals refer to this as the downshift cable adjustment. This corresponds to the throttle linkage adjustment on a TORQUEFLITE. Downshift cable adjustment should be checked with the engine running at the correct idle speed, 600 RPM. Adjustment is correct if the distance between the cable stop and the end of the threaded outer cable adjuster is from 30 thousandths to 60 thousandths. If the adjustment isn't correct, back off the cable adjuster lock nut and thread the cable housing adjuster up or down until the spacing is correct. Tighten the lock nut to hold the adjustments.
If the crimped stop on the cable is moved or been disturbed, or if a new cable is installed, you'll have to connect a pressure gauge to get the correct cable adjustment.
How do you go about that?
Connect the pressure gauge to the tapped pressure takeoff hole at the rear of the transmission. Because the frame crossmember gets in the way, you'll need this special right angle adapter. You'll also have to connect a tachometer so you can check pressure against engine speed. Shift the transmission into park and run the engine until it and the transmission are up to operating temperature. And while you're waiting, chock the rear wheels and apply the handbrake. Shift the transmission into drive and note engine speed and transmission fluid pressure. Engine speed should still be 600 RPM. Next, increase engine speed to 1100 RPM. Keep one eye on the tach and one on the pressure gauge to watch pressure increase as engine speed is increased to 1100. It's important to have those rear wheels blocked because the transmission's in gear and you don't want it to jump through the wall. The pressure at 1100 RPM should be 15 to 20 pounds per square inch, higher than it was at 600 RPM. If the increase in pressure is less than 15 pounds per square inch, thread the adjuster away from the cable stop. Turn the adjuster the opposite way if the pressure increase is more than 20 pounds.
The details and specifications for adjusting the Colt throttle pressure are different, but the procedure is so similar to Cricket you won't have any trouble. Besides, you'll find the details in the Colt manual and in the reference book.
On Cricket, the transmission selector cable adjustment is made at the transmission end of the selector cable. To make this adjustment, remove the clevis pin and loosen the clamp bolts. Move the manual valve lever as far forward as possible so that the valve is in the park position. Also, shift the selector lever into park. Next, hold the manual valve lever forward and reconnect the clevis to it. Pull the outer cable backwards lightly, just enough to remove all slack, and tighten the 2 clamp bolts. Be sure and check all selector positions to make sure the selector lever clicks into place for